Here we are again with ellipses, guys. So here's an ellipse, this black ellipse, and a point M on its boundary that I can move at will, right? Now let's pick a second point P also on the same ellipse that I can also move at will. And M and P define, of course, a family of these dashed blue chords. Now let's consider the motion of the midpoint of these chords. What is it tracing out? It's actually tracing out an ellipse. Okay, and this ellipse is half-sized, meaning that its semi-axes are half the size of the semi-axes of the original ellipse. It passes through the center of the original ellipse, and its center is at the midpoint between M and the center of the original ellipse. So you can see here that the midpoint is sweeping out this midpoint locus, the blue ellipse. And of course, if I move M around, I'm going to get a family of half-sized ellipses with the properties that we just described. Now, so far, there's nothing really new here. Now, let's consider a nonlinear phenomenon here. I'm going to turn off the construction line, and I want to ask the following question. Out of all points on the blue ellipse, which one is furthest or farthest from M? Okay, so let's draw. I'm going to compute that internally, and I'm going to report that, hey, I've gone through all the points on the blue ellipse, and I found out or figured out that F is the farthest one. So this is the longest chord across all chords, all possible chords in the blue ellipse, where one of the endpoints of the chords is M. Okay, so now I can play the same game. I can move M around, and I can watch what this chord is doing. Oops, it's doing a discontinuous jump here. We're going to talk about this in a little bit. But for most points, for most M's on the ellipse, the motion of F seems to be pretty continuous. It's only when M approaches either the bottom vertex, like so, that I have this discontinuous jump, or conversely the top vertex, where I experience a similar symmetric phenomenon of discontinuous jump. So let's draw the locus of F over M. Actually, before I talk about the locus of F, I just want to talk about a property of F. F is going to be such that the normal to the blue ellipse, or of the blue ellipse at F, is going to point toward M. And this has to be the case because we are at a maximum, a distance maximum. So dynamically, as I move M around, okay, you can see that the normal to the blue ellipse at F is always facing M directly, okay? All right, so we get this dynamically. Very good. So let's draw the locus of F. Locus of F, let's make my ellipse be have an aspect ratio of 1.5, which is my standard favorite aspect ratio, and then later we can wiggle that around. So this is the locus of that furthest point F as I move M around. You can see that it looks like these 4 fish hooks. It has a sort of hooky side here toward the end, and there's 4 of them. Okay, now for me to cross over to the other side, you know, I'm on this branch here of my locus. For me to cross over to the other branch of the locus, I necessarily have to make M pass through the top vertex. So let's do that. So when I make M pass through the top vertex, I have this discontinuous jump from this branch to that other branch. Now, is my locus always 4 hook shaped, or you know, is it always comprised? Does it always comprise 2 branches, each one of them having 2 hooks like this? Let's, for example, go up on the aspect ratio, and let's see what happens to the locus. The locus, at some point, loses one. It's 4 hooks. We still have a discontinuous jump from this. Let's animate M. Let's make M slide or glide through the stop arch or arc of the ellipse, and let's watch what's happening to F. So as I approach the top vertex, I get to the tip of my right branch of my locus, and then suddenly I jump to the other side. So let me just go back a little bit so we can see that jump step by step. I'm over here, right? M is on the left side of the top vertex, and as soon as M crosses the top vertex, it's going to happen just about now. F jumps to the other side. So let's just let this thing get animated over the entire ellipse. I'm going to remain on the left branch, and then when M crosses the bottom vertex, I jump to the other branch. Okay. Now, of course, if we go back to 1.5, I go back to the 4 hooks, and I'm going to jump right here, jump, go to the left branch, and jump again. Okay, now an interesting phenomenon happens. Let's draw that normal again. Okay, let's draw that normal again, and let's bring M to be pretty close to the bottom vertex of the ellipse, right there. Okay, now what happens if I further decrease the aspect ratio of this ellipse? Okay, so it's at 1.5 right now. Let's take it to 1.45, 1.44, 1.43. You can see that I'm still going to be jumping discontinuously. So you can see here that I'm still sweeping the branches in a first moment in a continuous manner, and then as the M approaches the top or bottom vertex of the original ellipse, I'm going to get closer and closer to the tip of these 4 hooks, of one of these 4 hooks, and then I'm going to jump. So the jump is still occurring here. Okay, let's go back in time here. So I'm almost at the top vertex, and right about now I'm going to jump to the other side, right there. So I'm still jumping. Okay, now as A over B approaches square root of 2, so I'm at 1.43 right now. Let's go to 1.42. I'm going to get to a situation where those 2 normals, okay, that graze the boundary, or let's say the two normals, or the 2 points F and say an F prime over here, that corresponds to the furthest distance from M. These 2 points are going to be closer and closer at a distance which is exactly twice the semi-axis of this small ellipse, and twice the semi-axis of the smaller ellipse is equal to the semi-axis of the outer ellipse. So let's go down to now 1.415. I'm further in, and at exactly square root of 2, I'm going to type it in here, at square root of 2, when I'm at 90 degrees, meaning M is at the top vertex of the ellipse, the distance between M and the bottom vertex of the blue ellipse is exactly equal to twice its semi-axis. Okay, so this is probably related to osculating circles. And at this point, though it looks like an artifact, I'm going to have converted my original discontinuous locus into a 4-leaf clover that is no longer discontinuous. So what I'm going to do is I'm exactly at square root of 2. Let's go a little bit below that, and so we can actually close this 4-leaf clover, and we can now watch what's happening to my locus as I traverse the ellipse. I'm not drawing the osculating circle, but you can be sure that this phenomenon of the 2 normals coming close together and avoiding the jump is related to that. So now you can see that I have a perfectly continuous traversal of, or the locus of F is perfectly continuous. Of course, if I further reduce the aspect ratio to 1.2, my clover becomes even smaller, 1.1, and as I approach the circle, the locus of F becomes an ever decreasing 4-leaf clover at 1.05 of aspect ratio. Now this tiny 4-leaf clover, and of course at the circular configuration, the perfectly circular configuration, let's go to 1.01. I end up getting that the furthest point F is basically diametrically opposed to M. Okay, so going back to 1.1, 1.2, 1.3, 1.4, where somewhere around which the transition occurs. I'm still at a continuous situation here. Ignore these discontinuous jumps. They're just graphical artifacts of the way Mathematica calculates these loci. But at, say, 1.5 or 1.6, I'm fully discontinuous. So I guess a question I have here is, what is there an expression for these curves? Are they algebraic? What do they look like? And can we get confirmation that indeed at square root of 2, A over B equals square root of 2, is where these four hooks or four hooked curve becomes a closed continuous four-leaf clover. What's of course the expression for this curve as well.